Good morning. It's great to have you here, and I'd like to welcome you to this presentation of the MIT Future of Solar Energy Study. I'm Robert Armstrong, Director of the MIT Energy Initiative. We are a cross-campus initiative at MIT charged with bringing together the entire campus, so all 5 of MIT's schools and a large number of faculty, our 1,000 faculty across campus. In our case, we engage about 300 of the faculty in thinking together about how can we address the world's great energy challenge. In doing this, we mean to bring together the science on campus, technology, and policy to transform the world's energy systems. One of the really important roles of MIT is outreach, and that is how do we take the work we do in analysis and research in technology to inform public discussion about energy options as we go forward. An important part of that has been a history of doing future of different kinds of energy studies. The solar study that we're going to talk about today is the 7th in an ongoing series of this nature. It's important to keep in mind that today we face a set of dual drivers in our energy challenge. The first of those is a projected doubling of energy demand by mid-century, by 2050, driven by a combination of factors. Chief among those is population growth globally and also increase in standard of living, GDP increases around the world. Coupled with that projected growth in energy demand is the urgent need to deal with climate change, which will require that we get carbon out of our energy system. So those are the dual challenges we face, doubling energy supply to the world and at the same time removing carbon from the system. This Future of Energy studies has looked at a variety of different technologies that could help us get to that kind of future. This series began in 2003 with the Future of Nuclear Power study, I think reasonably so because nuclear is the only zero-carbon energy system that has been deployed at scale globally. We've done a series of additional ones, as you can see on the slide here. The most recent was the Future of the Electric Grid, which addresses in particular an infrastructure need for renewable energy. Today we talk about the future of solar, and solar is a technology that is clearly key in this series because of its vastness on the one hand, which matches up well with the projected doubling in energy demand, but also the fact that it is a very nice zero carbon energy source. And so solar is certainly a technology that needs to be part of this discussion about how we meet the world's energy needs going forward. So doing this is going to require us to get solar technologies down to reasonable cost, and we're going to talk about that today. It's going to require thinking about what are the right policies to allow us to increase the role of solar by many times over, 50 times maybe by 2050. And those are the kinds of issues we want to examine in the presentation today, and those are issues that are discussed in much more detail in the study which you received as you came in. Before we get into the presentations in detail, I'd like to acknowledge in particular the very important role that an external advisory committee for the study has played, and to recognize a couple of the external advisory committee members who are here today. We're delighted to have Phil Sharp here. He chaired the External Advisory Committee. Phil is the president of RFF, also former congressman from Indiana. So welcome, Phil. Also, happy to acknowledge Phil Deutsch, David Goldwyn, Robert Margolis, Gary Rawl, and Bruce Sohn. I believe they're all here today, and I want to thank you all for what you've done to help us achieve the best product possible in this study. Also, I'd like to recognize the solar study team, or at least in part, here seated with me on the dais. Richard Smolensky at the far right, from my point of view, your left, is the chair of the solar study. He's the Howard Johnson Professor of Economics and former dean of the Sloan School of Management at MIT. Next to him is Vladimir Bulovic, who's the co-chair of the study. Vladimir is the Associate Dean of Engineering at MIT for Innovation. He's also the Farabros Massey Professor of Emerging Technology, and also somewhere in there a Professor of Electrical Engineering and Computer Science. Next is Frank O'Sullivan, who is the Director of Research and Analysis at MITI. And those first three will do the presentation this morning. But I'd also like to recognize the other people at the table who have been very active participants in the whole study, and they will be here to answer all the questions you have from Vladimir, Dick, and Frank's presentations. So if I proceed down from Frank, Robert Stoner, who is the Deputy Director of the Energy Initiative, Henry Jacoby, Professor Emeritus of the Sloan School of Economics, Ignacio Perez Arriaga, who's a visiting professor at MIT in the Engineering Systems Division, Robert Jaffe, a Professor Emeritus of Physics, Joel Jean, who is a graduate student, PhD graduate student in Electrical Engineering and Computer Science, and last but not least, Patrick Brown, who is a PhD graduate student in physics. So with that introduction, I'd like to turn it over to Phil to say a few words. Phil.
Well, thank you very much, Bob. I'm delighted to be here. Frankly, as a former member of Congress, I'm happy to be invited just about anywhere. But it's particularly an honor to be engaged with this extraordinary team from MIT. And as you saw the list of reports, many of you from here in the Washington community know that in virtually every case, it has had a significant impact in the Washington discussions within the federal establishment, with the executive establishment, within Congress, as people have debated and sometimes made decisions about policy. I just want to very quickly say that I think this report will be especially significant for several reasons. One is its central message that over the decades ahead, solar can play a very significant role in our energy mix here and abroad. Secondly, it's very important because of its comprehensiveness. Their interdisciplinary team means that they examine very carefully, as they have a long-standing reputation at this university, of examining technologies and what can be done with them and what's possible. Secondly, they've examined very seriously what's happening in the marketplace for how solar is actually being utilized today here in America and around the world. And thirdly, they've examined what are the policies in place or possibly to put in place that have incentivized the use of this technology. Their timing is extremely important because, as many people in this room know, there are debates going on and decisions being made here in Washington. They're being made in the state governments around the United States and in other countries as well. And as people argue over what is the potential and what is the right approach here. And of course, they have given in here a number of recommendations on how we ought to use our limited research dollars going forward to advance the technology, how we might adopt at state or federal levels the policies where we get the most bang for the buck out of them. And these are going to be things that I think will unquestionably be quoted in forums all around the country. But let me suggest to you very quickly, it's been an honor to be a part of their advisory panel. But what that really means is these folks did the hard work. Those of us on the advisory panel were assembled partly to bring a whole diverse set of interests and points of view so that they could ground truth what they were doing, test theories, and test their conclusions about various data. But we were strictly advisory. We didn't direct the research, we didn't do the research, and we didn't approve the report. So there may be individuals on the outside panel who may have differences with specific sections. But I think all of us found it an enormously educational and a valuable thing to do, and we appreciate the extraordinary work that you folks have done. Thank you.
Thank you.
Thanks very much, Phil, and thanks again for all the hard work that you did on this. I'd like to now to start with the presentation. Before Frank comes up to the podium, I'd like to suggest that we'll do the Q&A at the end of the entire presentation. But as we're going through the presentation, if a question arises, please jot it down on one of the cards that's at the table. You all have cards and something to write with at the table. And if you hold it up, someone will come around and pick those up, and we'll use those during the Q&A period. So thank you, and Frank, I'll turn over to you.
Thank you, Bob, and thank you, everyone. It's a real pleasure for us to be here today. So in terms of my remarks, what I'm going to do is provide a little bit of context with regard to where we are today in terms of the solar industry, its scale, and elements of like that, which are very important in establishing some of the groundwork for the recommendations that our study presents, and which will be discussed in greater detail by both Vladimir and Dick following on. So to begin, I think the most important context really for our study is the fact that solar energy represents a particularly important tool for addressing our climate challenge. And it does so because it is a resource with the scale and the broad distribution that makes it one of the very few low-carbon, low-emission technologies that truly has the potential to meet the scale, to meet the demand for future electricity globally, even in a scenario where we envisage significant economic growth over the coming decades. The map that we're displaying here just illustrates the annual average solar irradiance globally and how it's distributed. And there's just one important takeaway that I'd like to emphasize. If you look at those regions of the world where today we predict significant growth, significant new demand for electricity over the coming decades, you will see that those regions also happen to have robust solar resources. So regions like China and regions like India. And that's really why this is that's one of the reasons why this is a particularly important pathway going forward. In terms of scale, I also particularly like this little snippet of information to emphasize just how large this resource is. If we took today's technology here in the United States and we decided to generate all of our current electricity needs using solar energy, we could do it with less than half the area that we're currently dedicating to the production of corn ethanol. So it's a really, really, really enormous and really well-distributed resource. Now, we have two pathways available to us in order to generate that electricity. Solar photovoltaics, PV, which is generally the more commonly known, and concentrated solar power, CSP. PV is by far the more mature of the two options. Today it represents by far the largest portion of globally installed capacity, about 97% in fact, or about 200 gigawatts. And it's a beautiful technology in the sense that its technical conversion efficiency is not linked to scale. So a solar panel on your roof can be just as efficient technically at converting some solar energy to electricity as one in a large utility scale array. There are, of course, issues of economics of scale in terms of balance of system, and we'll discuss that later. However, photovoltaics have the drawback that they respond immediately to changes in the insolation level. So it is this inherently intermittent resource. CSP, on the other hand, it's a less mature technology with significantly less deployment globally, and it is a technology where scale does matter in terms of capital cost, technical efficiency, and so on. Additionally, CSP requires clear skies, so it works on direct solar radiation. So that limits, to a certain extent, locations where CSP is suitable. However, it has a distinct advantage in the sense that it is a technology for which adding storage is relatively easy. Now, the past decade or more has been a remarkable time for the solar industry here in the United States and indeed globally. If we look since 2000, we'll see that that annual additions of grid-connected solar generating capacity have been growing at about 40% since 2000. Really very, very significant growth rates. And here in the United States, I would argue that the story has been even more remarkable. Since around 2008, we have seen our installed PV grid-connected capacity grow from less than 1 gigawatt to more than 18 gigawatts at the end of last year. We have an additional 2.2 or so gigawatts in CSP facilities. The graphic on the left, it just illustrates the distribution in terms of the types of systems that we're deploying today, and you'll see a pretty broad spread. Residential systems, of course, representing an important portion of current deployments, commercial systems. But certainly today we're at a point where large ground-mounted utility-scale facilities are dominating in terms of what's deployed. In terms of geographical spread, California, of course, dominates. They were early adopters, certainly. But increasingly, we're seeing adoption at significant levels in other parts of the country. I think this is quite a startling statistic, actually. I think it really represents or illustrates the fact that solar has certainly moved through its nascency as a sector. Last year, up to a third of all new generation capacity added in the United States was solar. Now, with that said, with the very exciting scale-up that we're seeing, it's very important to realize that solar is still a very, very small contributor to actual generation. Here in the United States, and indeed globally, it only represents around 1% of total generation. And it's important for us, in the context of this study, to ask the question, well, can we envisage these growth rates that we've seen over the past few years continuing at the levels necessary in order for solar to ramp up by 50x or more by mid-century in order to meet that climate challenge? And I think it's important to reflect on the drivers of our growth to date in order to consider what the future might hold. The first very important point is the ramp-up in capacity that we have seen here in the United States over the past number of years has coincided with very, very impressive improvements in the costs, reductions in the costs of solar systems overall. And in particular, a lot of progress has been made in reducing the cost of photovoltaic modules. So the graphic on the right, the bottom line in green, illustrates the trajectory for the price of solar modules since 2008, and we have seen a remarkable 85% reduction in that number. And along with that reduction in the module price, the other associated balance of system elements, the other bits and pieces that are critical to putting the system on the roof and then financing it and so on, these costs have also reduced. However, the progress in that regard has not been as impressive. The other important point is that, of course, deployment subsidies have played a very important role. Both federal and state support has played a very important role in stimulating this growth. Next year, at the end of next year, we're looking at the ITC expiring at the residential level and being reduced very significantly at the commercial level. There are questions regarding what that means. And of course, there's increasing discussion and debate with regard to issue of rooftop solar and cost allocation at the residential level. And that really leads to this message. We've seen prices dropping. That's been a very encouraging dynamic. However, it's important to appreciate that continued rapid growth in solar is not an inevitability. So let's very quickly reflect on where we are today in terms of these cost gains and what that means in terms of solar's competitiveness more broadly in the electricity sector. And very simply where we are is that at the utility scale today in certain parts of the United States, PV is increasingly competitive with other benchmarks, combined cycle natural gas plants, for example. And we illustrate that at that point here on this graphic. On the left, we have the EIA's estimate for the benchmark combined cycle gas plant's levelized cost of electricity. So over its entire lifetime, what price is really needed, what electricity price is needed in order to make this plant competitive. And we contrast that with our estimations based on relatively contemporary system pricing for the levelized cost of electricity from a range of photovoltaic and CSP plants of different scales and in different locations. And you will see that in California, at the utility scale, increasingly the utility scale systems are looking relatively competitive. I would add, and progress has been so rapid in this space in particular, that further price gains since we established these benchmarks make this picture look even a little bit better. However, just because it's working well or it's increasingly competitive in California doesn't mean that that's a ubiquitous story. In Massachusetts, for example, utility-scale solar is not a particularly compelling option yet. And residential systems in either California or in Massachusetts are still particularly expensive. CSP at the utility scale, well, it's really just a utility scale play, but in California, it's not quite as competitive as utility scale PV. And I think that's a reflection of its maturity, but it's certainly making progress. We included Massachusetts-based CSP here just to illustrate that CSP doesn't work so well where you have a lot of clouds. Now, that snapshot of the economics is really a reflection on today's economics, where solar is a marginal element in the overall system. Going forward, if solar is to play that much more significant role that it needs to play in the electricity system, the economics of solar face some challenges that are important to appreciate. In particular, as we move more and more solar onto systems, very significant generation during midday hours and so on, when the solar resource is very high, will suppress wholesale market prices. And that will have two effects. A very positive effect in the sense that it will reduce average market prices for everyone. But for investors in solar, the return that they will receive and the prices they will receive will be lower. And as we move more PV onto the system, those prices will continue to fall. And that's important because it really emphasizes the need for us to continue to focus on driving costs lower and lower and lower. It's a very, very important point that we're going to emphasize again and again in this presentation. In addition, because PV specifically is not a dispatchable technology, much larger penetration will lead to some challenges with regard to grid integration and so on, which must also be addressed. So in light of this context, the question arises, what needs to be done now to make it more likely that solar's really, really significant potential can be realized? And in our study, we have three main messages. The first message is that federal solar R&D policy must focus on transformative technologies that promise the dramatic cost reductions that we will really need in order to make that very large-scale deployment economically possible. The second message is that federal and state authorities must prepare for much greater penetration of PV generation. There are technical aspects to this message, and there are going to be regulatory aspects to this message, which we will discuss. And finally, our third message is that federal, state, and local support for solar deployment really needs to be reformed to ensure that we're getting as much solar generation as is possible per dollar of support provided. So with that, I'm going to hand it over to Vladimir, who's going to provide some greater detail on message one.
While we're changing, remember to fill out those cards with questions and hold them up, right?
All right. So the first message is regarding the technology. Indeed, if we look forward and ask what is going to be needed a decade from now from the solar, it's going to be different from what it is here today. If we asked that same question a decade ago, the investments we made a decade ago led us to the successes of what we observe right now today. So we look at the federal solar R&D spending, at federal solar R&D policy, and ask what should we support to transform the present systems of solar in order to enable us to drive the cost down even further, not just for the module, but for the entire system. The present systems, the present technology, and I'll describe it in a moment, indeed is very mature. The abilities to generate very efficient photovoltaics is indeed extraordinary from perspective of modules. Ability to further drive the cost of modules will not be as significant as the focus on how do you integrate those modules into the larger systems that produce electricity, and hence leaving the idea of what modules can do, leaving it to the industry that is indeed invested in being able to deploy those modules would be a very rational thing to do. Second thing to suggest would be to identify what next technologies can we imagine might be needed. And indeed, I'll focus primarily on photovoltaics, as those are the dominant solar technology. I will touch upon concentrated solar power in one slide towards the end. The king of the hill, the dominant technology in the solar world, is solar photovoltaics based on crystalline silicon. This is an extremely efficient technology near its practical limits. It's highly reliable. It has been field tested for decades. It's robust. It's durable. It has abundant material source, silicon, as the primary material from which it's built. It's non-toxic. These are all fantastic qualities, indeed qualities that we see as why the technology has been able to propel itself as far as it can. The challenges, though, of this technology rely in the way that you might choose to integrate it in the greater system. Primarily focus on the hardware of the balance of systems, integration in the field. Disadvantages come from the fact that because silicon is the material, it's needed to have a relatively thick wafer of silicon in order to absorb a sufficient amount of light to generate electricity, which leads to the need for heavy glass substrates to support the silicon rigidity of those glass substrates in order to allow the deployment as we now see it. Consequence of that is that manufacturing, although dramatically streamlined, is still more complex than what we can imagine for the next generation of solar technologies. So our conclusion is that crystalline silicon PV technology is efficient, it is mature, but its intrinsic properties may limit the potential for much further system cost reductions. And focusing on the system cost reductions will allow us to take the next step in our cost reductions. All right, well, if you look at the actual costs that you will incur in installing a silicon system, there is a module cost, and that's the red bar on the left. And then in the middle are what we call the balance of system costs, inverter and other hardware, engineering, construction, sales tax, margins, and G&A, overall leading you to the full system cost that we see on the right. And indeed, it is higher for utilities than for it's higher for residential scales than for utility deployment, because at residential scale, you have to optimize it for a specific house in a specific way. All right, well, looking then at that balance of system costs that dominate the total system cost, industry indeed has the ability and the incentives to reduce the BOS as long as conventional silicon technology is used, as that is the one that we have perfected our understanding of. Government's, though, role needs to continue in both convening and organizing. That's to say, highlighting the need to drive the BOS cost down and addressing things like the soft costs, but from R&D perspective, addressing the integration hardware costs, the ability to actually deploy a technology like that, or reimagining what the deployment and hence reduction of BOS costs could be. So what are our opportunities? Well, the opportunities that have been identified already is the use of so-called thin film technologies to replace silicon technologies. And as a very simple graphic, this picture on the right shows a cross-section of a typical silicon wafer versus a typical thin film technology. The dominant thin film technology is based on cadmium telluride versus silicon. Notice it's extremely thin, hence it might yield itself the ability to be flexible except for a couple of things. Cadmium telluride is a high temperature process of deposition, as a result necessitating high temperature substrate, glass. Again, going back to the challenge of silicon, a heavy substrate that will contain this particular material set. The other thing is, if you look at the actual availability of a thin film that can be streamlined deposited and hence made into a solar cell like cadmium telluride, the challenge is really in the availability of the material set. The graph on the left, on the y-axis, vertical axis, shows the amount of time that would be needed to mine enough material to make a particular solar cell technology. It starts down in hours, then days, then weeks, months, years. It's a logarithmic plot, up to 1,000 years up on the top. Well, the goal is by 2050 to reach significant deployment, about 35 years from now. How much time would we need to mine silicon to reach 100% of electricity needs with silicon? It would be about 6 years of mining silicon, and we'll be able to get there. How many years would we need to mine tellurium to do the same, to make a cadmium telluride solar cells? About 1,400 years, given today's ways we indeed mine for it. So the challenge clearly is that some of the commercial thin film PVs that are streamlined in the way they can be produced are not scalable and don't necessarily address the balance of system issues that are inherent in the uses of heavy substrates such as glass. Do we have other thin film technologies that could indeed give us the benefit of the thin film but eliminate some of the challenges in materials availability and in the high temperature processing? And the answer is a yes, absolutely, except these are young technologies. Utilization of so-called CZTS, perovskites, quantum dot PV technologies, these are new technologies that are providing reasonable performance when it comes to their efficiency. Indeed, if I ask how many years would it be needed to mine enough material to deploy them, all of them come to less than 3 years, typically. As a result, we can say, well, this is indeed abundant material set. Temperatures, yes, they can be near room temperature deposited in some cases, allowing us to imagine extremely lightweight, rollable, flexible formats, and hence reimagining what the balance of system integration would look like. How thick is this technology? Even thinner than a typical thin film cadmium telluride technology, and just for comparison, that's a cross-section of a strand of hair, just to get you a sense of how small these things are. We have an ability to manipulate nanoscale and provide us these incredible performances. However, these are young technologies, but ones that provide an opportunity to make light and flexible structures. One of those demonstrated in 2012 is a solar cell there on the left, upper left. It is wrapped around a strand of single hair, just to demonstrate exactly how lightweight and thin it might be, micrograms, right, per square centimeter. You can imagine high throughput, again, scaling down the manufacturing floors from very significant sizes to sizes of fields, simple football fields, right, to produce as much as needed solar over a relatively short amount of time. Amount of materials available, yes, very abundant. Production is indeed today such that we could come up with a way to make enough material for these new technologies very, very rapidly. But current challenges are, these are low efficiency cells, relatively speaking, to what silicon has achieved. They are, relatively speaking, low stability. We haven't shown 20, 30-year deployment in the field or stress conditions, and unproven at scale. For all of the pictures of where we might be heading, these are pictures of where we might be heading as opposed to real field demonstrations, allowing us to say that if this can become reality, just as we were dreaming of silicon becoming reality we see today, we need to start investing today so that in half a decade away, we could actually start recognizing the opportunities of these new types of technologies that at this point appear to be more deployable and at this point should allow us, we think, to reduce the BOS systems of installation. Consequence of that is we need to understand it and study it, and much more R&D needs to be done. And this is where we think federal solar R&D should be focused on. I'll just for a moment also focus on concentrated solar power technology, as it provides an entirely different way of thinking how to scale solar collection. Starting with total incident energy, that's on the left, you need to absorb it. It comes in the form of heat. That absorbed heat from sunlight can indeed be used to turn a turbine, and that turbine turning can generate electricity. The efficiency of that conversion, in this case, let's say, leads you to about 17% generation of electricity, gross, net about 16%. So start with sunlight, collect the heat, turn the turbine, and make electricity. A very powerful system, a system that actually has a plenty of opportunity to be further optimized. For example, more efficient solar collectors would certainly be extremely valuable in this particular technology, being able to indeed utilize more of the incident light. Next, looking at this conversion process, today's processes that are utilized are by no means the most optimal ones. We do know that further investigations of both material sets and conversion processes at higher temperatures would be a very valuable way to further increase the efficiency of the systems. And one other extremely important point, remember we collected sunlight to generate heat. We can store heat. Heat can stay around overnight when there is no sunlight and can be used when needed to form a dispatchable technology. So the benefit of CSP is indeed the ability to store the heat that can easily, or call it, that can naturally be built into the system of the CSP. So we have hence looked at the present DOE solar R&D funding. And mind you, we are focusing on technology. That's why we talk about research and development in technology. And have asked, are we looking today within the DOE budget towards the investment in the new sets of advanced solar technologies, or are we focusing on deployment and of the present, current technologies? And if we look at the projected budget, this is 2016 is projected, everything else is historic. 2016 budget and before indeed emphasizes current technologies over the development of the advanced solar technologies. Indeed, we do believe that focus on the advanced solar technologies would be extremely valuable for what's going to happen 5-10 years away from today. So our key technology recommendations are the following. In the PV world, the federal photovoltaic R&D should focus on transformative technologies rather than on near-term reductions in the cost of dominant technologies such as crystal and silicon systems, as indeed industry has an incentive to push in that way. Federal photovoltaic R&D efforts should also focus on new and emerging thin film PV technologies that use environmentally benign materials, earth-abundant materials, and that are compatible with low-cost manufacturing and lower, hence, the BOS system costs. On the CSP, federal CSP R&D efforts should focus on new materials and new system designs, and should establish a program to test these new designs at pilot-scale facilities, akin to the way that commonly done in chemical industry for chemical manufacturing, hence allowing us to experiment at a pilot scale with the opportunities in redefining what CSP can be. I will invite my colleague Dick Schmalensee to tell us about the remaining two messages.
Thank you, Vladimir. So our second message is the need to prepare for greater PV penetration. We focus on PV because crystalline silicon photovoltaics is likely to remain the dominant solar technology for at least the foreseeable future. Having a lot of such generation in the system poses integration challenges that storage could solve. I'll point out there are other issues as well. And finally, again, I'll talk about the retail level, where retail pricing needs to be reformed to avoid unnecessary political resistance to distributed generation. So this is a picture, for those of you who know the California duck chart, this is a variation of that chart. It illustrates predictable variation in solar generation and its implications for the rest of an electric power system. The top line, which is the same in all the charts left to right, is electricity demand in a typical day in ERCOT in Texas. And the different pictures show the impact of different amounts of solar capacity added to that system. So the yellow is solar generation, the brown is non-solar generation, adding up, as it must, to total demand. You notice a couple of things. First, look at the peak, the highest level of non-solar generation, the peak of the brown section. That doesn't change much as you add a lot of solar electricity, because the peak demand occurs later than the peak solar generation. It goes down a little if you have a magnifying glass, but after a while, you're not contributing much to the system's capacity. The amount of non-solar generation isn't going to go down much when you add a lot of solar. The second thing you might notice, particularly on the right, where we talk about increased ramping, after a while, the amount of generation from the non-solar part of the generation fleet declines dramatically as solar generation ramps up, and then it has to come back up when solar generation ramps down. That requires a fair amount of flexibility. The Texas fleet has a lot of coal plants in it, for instance, and they don't handle that very well. So either there are higher costs that they have to deal with, or the fleet has to change, or some mixture. Now, in a way, this is the easy part. This is market forces will adjust to make this happen, but the system will have to change. In a way, the harder part is illustrated by this chart. This is hourly solar radiation every hour of the year in 2012 at Golden, Colorado, where there happens to be both pretty good sunlight and very good data. So you will notice the white intervals as you go across hour by hour. That's night, of course. And as you go down, you see there's more black area in the middle of the chart than at the top or the bottom. That's summertime. So that's predictable. What's less predictable are the variations within and between adjacent days, and that's weather. If you go across in May, for instance, you will see about, 3 really dark days, lots of sunlight, followed by 2 days of almost no solar radiation. Storm front, clouds, something of that sort. So a system with a lot of solar has to be able to cope both with the predictable variations, which is sort of what was illustrated by the previous chart, and by the less predictable variations. Now, at the kinds of levels of penetration that we've experienced so far, this is not a profound problem. We can do it with globally 1%. Germany gets about 7% of its electricity from solar, and Germany can handle this without dramatic measures. There's demand response, there are a variety of other things. But it's our view that at high levels, if you think about 25% of electricity being generated by solar, and by mid-century, those are the kinds of numbers people use, it is hard to see how that can be done with this kind of pattern of output without economical, scalable, megawatt-scale storage. And let me just say that the last bullet, despite the Tesla announcement, which is a nice evolutionary step, we're not there yet. We're not close to being there yet. The other thing I would say before I leave this slide is we had some comparisons of levelized cost. And levelized cost is a terrifically useful device to compare baseload gas with baseload coal, with baseload nuclear, say, because those technologies are dispatchable and in principle have a constant rate of output. It's much less useful when dealing with solar, which is why in an earlier chart we talked about how, in fact back in this chart, you can see what's going to happen is with high solar penetration, electricity will not be valuable in the middle of the day. That price goes down, and that's an important component of the return to solar generation. So levelized cost is a very limited use, and certainly levelized cost doesn't take into account this kind of intermittency. So we use it as a zero-order tool for comparison, but it is just that. So storage and R&D on storage becomes an important part of the strategy going forward. Now let me turn to the distribution network. Here is our most colorful chart. So one of the advantages of distributed generation, rooftop solar if you will, is it reduces line losses, distribution thermal losses, in the distribution system. And that's clear. But it also typically, beyond low levels of penetration, requires investment in the distribution system. Distribution systems are designed for one-way power flows out to residences and businesses and so forth with a lot of distributed solar. And certainly you see it in Germany and some places in the US, you get two-way power flows. Now, they can be handled. This is not deep science, but it requires money. And what this shows is the savings in line or the increase in investment necessary minus the savings and losses for a variety of different scenarios. We modeled different assumptions about what kind of distributed generation goes in, different assumptions about the layout of the city, and so on and so forth, different design standards. And the pattern is clear. There's a net cost of distributed photovoltaics. The investment cost outweighs the savings in electricity losses. Comparing residential with utility scale, then, residential has all of the intermittency and everything else that utility scale has, but it also requires this investment in the distribution system. I would also add, though it's not here, that one feature which people in Hawaii are experiencing in spades is the utility can turn off a utility scale system if it has excess generation. It can't do that with your rooftop. And that raises operational problems. That's a soluble problem, but it is not yet solved. Finally, I want to turn to everybody's favorite subject in this context, net metering. And this is an issue at the distribution system. Henry Jacoby was up late last night at a town meeting in Belmont, Massachusetts, where there was a ferocious and incoherent argument on this subject. So let me just sort of outline the basic economics and why we think it matters. So the first, on the left-hand side, you see set of utility customers. You can think of the width of these bars as measuring their consumption under a standard utility pricing regime, which means that their per kilowatt hour rate consists of the wholesale price plus a component, a distribution charge per kilowatt hour to cover, if you will, the wires, the cost of the network. That cost is not entirely fixed, but it's pretty fixed in the short run. So that means that if consumer A decides to sell power, consumer A gets the retail price. If a large-scale solar development wants to sell power, it gets the wholesale price. So for starters, this system provides an extra subsidy for rooftop or distributed generation. That may or may not be a good thing from society's point of view. It's kind of invisible, but it's there. The more difficult issue arises. Suppose that A installs a solar roof, and we've drawn it in an exaggerated form to let A be a net seller. So A is not covering her share of the cost of the network. So the first thing that has to happen is the rates of everybody else have to be increased to cover the net cost of the network. There may be an impact on wholesale prices, up, down, sideways, but the one thing that's unavoidable is those network costs have to be covered unless it is taken away from utility shareholders. That's the one thing. And they have to be increased a little bit more because, don't forget, A is getting the retail rate that it's not paying. So not only is A not contributing to the network costs, but in this picture, it is being paid what it would have contributed. Now, you may think that's a good thing or a bad thing, but people get upset about this. I live in a condo. I don't have a roof I can put solar on. If a lot of people put solar on their roofs, my rate will go up. I can't avoid that. Now, this has caused backlash in a variety of places. There are ferocious debates, not just in Belmont, Massachusetts. There have been ferocious debates in Arizona and in other places, and we see this increasing. I mean, you can say all you want about the virtues of rooftop solar, but the cost shift is real. And that cost shift is going to produce a backlash against distributed generation, which is probably not a good idea. Just as this is an unintended subsidy, it's an unintended backlash. So we have a number of messages, recommendations, but I want to focus on two of them here. The first is storage, economical, scalable energy storage is going to be crucial to achieving photovoltaic deployment at large scale. One naturally thinks about batteries, but if we had a cheap way to split water into hydrogen and oxygen, you could store the hydrogen. Thermal storage provides another vehicle, but storage is the key, we think, to sustaining large-scale photovoltaic deployment. The second is there really is a need to reform that retail pricing system. There's the unintended subsidy, good, bad. There's the cost shift, not perceived as fair. Again, even if I didn't live in an apartment or in a condo, I might think it was unfair. So those are our two recommendations there. Let me now turn to support. We support solar deployment in this country by an enormous list of policies, federal, state, local. We think continued subsidy for deployment is important. It really does lay the groundwork for future scale-up. But the way we're doing it, we're not getting the bang for the buck we should. We are wasting money. We think it's possible to reform the current system in ways that simply give us more solar generation per dollar of taxpayer or ratepayer expenditures. So let me walk through it. As I said, there's a wide range of subsidies. It's a long list. These subsidies, we talked about the balance of system costs. Some of those costs are going to be pushed on by companies deploying today's solar technology. Permitting costs, cost of dealing with regulation, interconnection rules. So having deployment ongoing today lays the foundation by giving experience with deployment, overcoming some of these institutional barriers, and providing manufacturing experience. So, particularly in the absence of a carbon price, there's a strong case to continue subsidizing deployment. We do it at the federal level, mainly. There's a long list of federal programs, too, but the main federal programs are an investment tax credit and accelerated depreciation. These are the investment tax credit is scheduled to be cut dramatically at the end of next year. We think that would be unwise because we think it would have a sharp effect on deployment, and we think continued deployment does lay the foundation. Besides whatever near-term benefits it has, it lays the foundation for a large scale-up down the road. But we think doing it the way we're doing it and just reenacting the investment tax credit would be wasteful. So let me say why. This is the picture we had before of utility scale and residential scale photovoltaic costs, here highlighting the subsidy in California or Massachusetts. And as it says at the top, this system is designed, no, not designed, has the effect of having the greatest subsidy where the costs are higher. Now, if there were some associated other benefit, that might make sense, but as we talked about, residential doesn't have greater external benefits, it has external costs. So if you look at California, and you see that the subsidy to residential scale PV is $72 a megawatt, and utility scale PV, $37. Well, that's because the residential system is more expensive, pure and simple, because the subsidy is a percentage of cost. Now you compare California and Massachusetts for, say, utility scale. Gee, Massachusetts gets a higher subsidy. Those are the same system design. Massachusetts has less sunlight, so there are fewer kilowatt hours produced from the same system. So the subsidy per kilowatt hour, which is related to the system cost, is higher. It is hard to make an argument that that's a sensible pattern. There are other problems with the current system having to do with the tax equity market and having to do with the way people who own the system on your rooftop can calculate their subsidies. But the main, which we're happy to talk about, but the main problems I would point to is simply this perverse targeting. Let me turn now briefly as we wind up to the states. States, again, have a huge number of programs. The most visible ones are the renewable portfolio standards. There are about 30 of them. 24 of them require solar generation or distributed generation. California, you'll see, doesn't show up as an RPS state, which strictly it isn't, but California has a wide variety of programs, like many of the other states, that support solar. The fact that they're all different is a source of inefficiency, but the main source I would point to is they have restrictions on siting. So Massachusetts seems to be interested, I'll pick on Massachusetts, seems to be interested in having people put solar generation on rooftops in Massachusetts, where it's not very sunny. As a national matter, if we were interested in subsidizing solar generation, Massachusetts wanted to pay for it, it would make sense to pay for solar generation someplace else. But we don't. So the fact that there are siting restrictions on all these programs raises costs. It's no accident, if you can remember that earlier graph, Massachusetts and New Jersey were big solar leaders. These are not sunny places. It's inefficient to have Massachusetts and New Jersey do more than New Mexico and Arizona from a national policy point of view. I'm big on states' rights, but that just is inefficient. So on deployment policy, again, I want to say we do support continued support for solar technology deployment. Drastic cuts of the kind that are now scheduled would be unwise. But if we're about generation, we should reward generation. It's hard to make a case for subsidizing residential solar more than utility scale solar. And for reasons having to do with the way they operate, there's a strong argument to avoid the use of tax credits. And finally, state renewable portfolio standard programs, from the national point of view, should be replaced either by a uniform program nationally, or siting restrictions should be removed or at least relaxed. So let me remind you of our main messages. We will now segue into Q&A. We want a long-term focus on R&D, emphasizing what the federal government can do that industry can't do, and that's the fundamental research at the next generation of technologies. We believe that it is important to do preparation now for widespread penetration of solar photovoltaics, because if we're going to meet the challenge of climate change, that will happen. And finally, we think it's unfortunate, particularly if we move to large scale, that our support policies are so amazingly inefficient. So with that, let me put up the list of study participants and invite questions.
So while we have this list of participants on the screen, I'd like to acknowledge in particular Renan Miller, who's sitting in the audience here, who's the executive director of the solar study. He's been extremely important to getting this done. So let me begin with a question on the recent cost decline that was observed in one of the very early slides, and how much of that is due to true technology improvement versus improvement decline in raw materials prices. Frank, do you want to?
Well, I think we can leave Vladimir take it.
Okay, all right, fine.
So there has been significant realignment of the industry towards the ability to produce better and more and solar with more efficacy. So the result of that, indeed, is the observed reduction in the costs. There's also been a tremendous scale-up of production outside of the United States. And that tremendous scale-up of production also has led, again, to the reduced prices, is actually maybe a fair way to say it, as opposed to the costs, which, indeed, one would argue there might not be very much profit, if at all, in actual making of the cells as, indeed, it costs right now external of U.S. to make them. So what we are observing is indeed lower price of the module. The actual cost of the module, we believe, is slightly maybe higher, maybe lower, but just about where the present price is, indeed eliminating the profits for making them. One way to ensure technology will keep on going, right, is to keep on reducing the cost. And understanding how to push the costs below what they are now really is what we are focusing on in what we are recommending to the government.
I expect most people here are aware that first the EU and then the US have argued that the Chinese are subsidizing, and there's a great deal of opacity there. The Chinese expanded capacity sharply, demand didn't expand as rapidly, there was excess capacity in China, costs went down. How much, if any, is the sort of subsidy that we've complained about, the government has complained about, is unknown to us, and we haven't tried to make a judgment on it. But I would just note that that issue is out there.
Good. So another question is, how do you estimate the time for these emerging PV technologies to reach commercial maturity? And a second part to that is, how have you totally given up on crystalline silicon?
No. So let me answer the second part. We are praising crystalline silicon successes. By no means are we giving up on crystalline silicon. As a matter of fact, crystalline silicon will be the dominant technology for the next decade, probably, when it comes to the ability of crystalline silicon to generate photovoltaic response. No, we are not giving up on crystalline silicon. We're actually praising it to the point to say it's been invested in, thanks to the investments that we've done up till now. Crystalline silicon has made this amazing progress. And it is a relatively mature technology broadly deployed by many industries. And that industry is ready to take it on, to keep pushing it forward, if at all possible. No, we are not giving up on crystalline silicon. What we are pointing to is that there is any new technology, like the ones that we have recently observed, a typical landscape for any hardware developed anywhere at scale is about a decade. I often cite that it took 15 years to develop a zipper from the first demonstration to large-scale deployment. I think Velcro took 17 years. So go ahead and look at microchips. I mean, microelectronics chips is about 15 years as well. Any technology needs a steady investment from the initial demonstration through scale-up. Because indeed you spend $1 on research, 10 on development, 100 on production, right? I mean, and the ability to actually get to that point, that's about a decade-long journey. We have some amazing demonstrations of brand new technologies. Technology called perovskites has, maybe just a couple of years ago, just came on the scene, already at efficiencies that silicon is able to perform at. Just out of the gate, the first demonstrations were that high up. And by no means is that technology tapped out. It happens to have issues with stability and issues with manufacturability. But from perspective of performance, it is tremendous technology. Silicon had issues with stability and manufacturability as well, right? And any other large-scale thin film technology had that before we figured it out. So how long? Give it a decade from where you start to where you're going to finish, if you're going to try to give it a chance to be deployed at large scale.
The first steamship across the Atlantic could barely carry enough coal to make it, let alone carry cargo. By the time steam became commercially viable, sailing ships had improved a lot. And you would have been crazy to give up on sail when steam first appeared. But you would have also been crazy to put all your bets on sail.
I'd just like to jump in for a second. I mean, to get away from the zippers and the Velcro, I guess. The examples for PV, I guess silicon has been around, since basically the date of the first invention or the first patent or first research paper, maybe the 40s. CAD-TEL, SIGs, 60s and 70s. Every single commercial PV technology today has been around basically for at least 30 years. So if you want to take that as a baseline, you could. Today's technologies, in terms of record efficiencies, are growing much faster. They're improving much faster than silicon did in the early days, than cadmium telluride, than SIGs. But they are still far from commercial deployment at large scale. So that's just a point of reference.
Yeah, so a follow-on to that is what you were talking about, Joel, is how low are current efficiencies for emerging thin films? And are there physical limits to that efficiency?
Sure. Yeah, so today's efficiencies range for the emerging thin films for, at the high end, I guess, perovskites. Those have jumped on the scene in the last 5 years, maybe the last 3 years. And those are up at around 20, some reports say up to 24%, which is quite good. Silicon's record efficiency is at 26%. Obviously, those cells, the perovskite cells, haven't been demonstrated in any modules yet. So we can't really say the efficiency of a module yet. The other technologies, quantum dots, organics, the records are around 10%. There's reason to believe that the efficiency limits for those might be a little bit lower than silicon, but it's hard to say right now. They're still early, young technologies.
Okay. So let me direct a question to Dick. Question is storage necessary for high PV penetration, or is it just helpful?
I think it's going to depend on the system, and it's going to depend on the level of penetration. Could we imagine a system that consisted entirely of photovoltaics and combustion turbines and a lot of demand management? Yeah, you could probably run that system. You might be able to do it without storage. We've done some work, Ignacio has done some work looking at the impact of storage on costs, looking at, say, California where there's hydro versus Texas where there isn't. And you see a clear implication, a clear effect. I think technically you could probably do very large-scale penetration without storage, but it would be tough. Let me give you an example. Suppose you actually want to get 70% of energy from solar. Well, if you build enough solar to do that in the dead of winter, you're going to have too much in the peak of summer, and you're going to have to shut it down. You're going to have to shut a lot of it down. That raises the cost substantially. You're going to have to do a lot of demand management, and you're going to run inefficient combustion turbines for a lot of the system. So I think at some point you do need storage. You can go very far without it, but expensively. So I think any realistic notion that you're going to get past 20, 25, 30% solar by mid-century without storage, I think might be possible, but is unrealistic.
Maybe I could just add one comment on that. I think, as Dick earlier pointed out, that storage doesn't have to take the form of batteries necessarily. It could take the form of heat or stored water. And in particular, outside our market, in the markets of Africa, for example, where there's a lot of reservoir hydro and the potential to build a great deal more reservoir hydro, there's the possibility of growing up PV capacity along with reservoir hydro capacity to create storage and flexibility in parallel. We did a study, which is described in an accompanying paper on our site, that shows that you can actually go to almost 100% nameplate PV capacity on the Kenyan grid, which happens to have a very high, or rather large amount of reservoir hydro, if you interoperate the hydros with solar. We do that at a different scale in this country and in many other countries around the world as well. But the point is that you can get by without waiting for technology to be developed. You can instead make investments in natural storage devices.
Yeah, well, the sources of flexibility, I think that should come from flexible generation, like gas-fired power plants, storage, but also interconnections, and smoothing out the impact of variability in solar by coupling different regions with good transmission and demand response. We hope that with the utility of the future, aggregation, information and communication technologies, we will be able to use many of those virtual storage that is not in batteries, but also in buildings and in industries and residences, etc.
Thank you, Ignacio. So this is a question that I would direct either Frank or Jake, and it's a question about what we use as a benchmark comparison in cost for residential solar. Question was, isn't this the retail power price rather than the LCOE of a combined cycle unit?
Well, that point, I think Dick discussed it in his discussion of the net metering issue. Today, certainly, if you are installing a unit on your rooftop, that is the comparison. The levelized cost is very, very zero order level kind of metric, but it's reasonable. You're comparing that with your utility rate, if you wish, as a benchmark. However, as Dick mentioned in his remarks, as we move to much more significant penetration at the rooftop level, there are a whole host of costs that must be accounted for. And we will see, it's not clear yet how they're going to be appropriately distributed, but likely, certainly politically, they will have to be accounted for and distributed in a manner that differs from today's rather basic net metering structure. And in that instance, the value of the energy generated by your rooftop will not be equal to your retail rate. It will be some point lower, and that's really the benchmark that you need to be looking at when you're considering a longer-term future where distributed solar may play a much larger role in the system.
I would also say that an apples-to-apples comparison in terms of output is utility scale solar versus residential scale solar. And residential per kilowatt hour is just more expensive. So from the point of view of society as a whole, while residential may be profitable given retail rates, given subsidy schemes, from the point of view of society, it is more expensive than utility scale. Not clear why we want to differentially encourage it.
Just one final point, perhaps it's a more personal point, but I would agree. I would suggest that I think most here on the panel would agree. We really have to ask the question, what is solar about? And our study, this study, is in the context of a carbon-constrained world. So we're looking at a future where we are dealing with carbon and reducing carbon. And in that instance, a kilowatt of solar is a kilowatt of solar, kilowatt hour of solar is a kilowatt hour of solar, no matter where it's coming from. And this then leads to these important benchmarks in considering utility versus residential and so on.
Okay, so we're about out of time, or out of time. I'm going to do one more question before we conclude. The question is relates to the third message, so I guess it'll go to you, Dick, and that is, what are the types of incentives that are needed? Can you give more specific or concrete examples of direction forms of incentives that we need to put in place?
Well, it's not hard to think of better systems than ours, but let me just mention one example. As I said, there's a huge website devoted to listing the incentives for solar and renewables in the United States. The German system you can write down on a couple of pieces of paper. It's a guaranteed return per kilowatt hour of generation from different technologies. Full stop. That's it. That's simple. It rewards generation, not investment. It treats utility scale and residential scale the same. Well, actually, the German system doesn't, but it could. They decided to subsidize residential more for reasons that I cannot begin to explain. But that's simple. That's called a feed-in tariff. That's one system. It's much more popular internationally than the kind of investment subsidies we do. A variation of that is an output subsidy or a premium tariff, which makes the subsidy per kilowatt hour proportional to the market price. So you reward generation more when it occurs. That differentiates, for instance, between wind and solar, since solar tends to generate in hours when electricity is more valuable. Wind tends to generate at night when it's less valuable. So that would differentiate between them. There are a variety of variations on these themes, but the main, again, internationally, the main message is focus on generation, not what it costs to build the thing, but what do you get from it?
Thank you. So in wrapping up, I'd like to just capture sort of the main message here that we think in this study that solar has a very bright future, if you'll pardon the phrase, that given the vast resource that we have and its intrinsic zero carbon nature, it seems inevitable that it's going to play a key role in future energy systems. And to help us get there, we've laid out in this study what we think are a number of key points that we need to tackle in the U.S. and perhaps elsewhere. One in R&D, a focus on transformational technologies to help move to the next level after the next 20 years, perhaps with crystalline silicon. Doing work at the federal and state level to enable or prepare the grid for massive scale-up in solar. And then lastly, reforming or rethinking the subsidies we use, as Dick described. So as we close, I'd like to remind you that the study itself can be found electronically on the MIT Energy Initiative website. We're very easy to find at MIT, web.mit.edu/mighty. And then secondly, I'd like to let you know that on that website, in addition to the study itself, you will find a variety of working papers that deal with other issues that we haven't had any time to go into here, or we didn't have space in the study to explore. For example, solar energy in developing countries, which Rob touched on very briefly. So thank you very much for your attendance and participation and questions, and we look forward to a bright solar future together. Thank you.